introduction, and thank you to the organizers for the opportunity to tell you about one of our projects that's going on in our program here in Vancouver, Canada. We actually have a pretty diverse set of interests in the group right now. We've been really doing a lot of work around robotics and automation and looking at ways to couple that to machine learning algorithms to build out these self-driving labs. And we've been focused on solar cell materials for the last couple of years around this, but we've actually are now building these out for CO2 utilization, which will be really the main theme of this presentation. But we're also interested in everything from like high risk, high reward projects like cold fusion to membrane reactors, which we're really excited about because it allows us to actually use electrolytically produced hydrogen to perform chemical reactions without ever actually going through an H2 gas intermediate, which is I think there's just a lot of opportunities around that concept. And then we're also interested in smart windows, but that's not been spun out as a company. But my story today is really going to be focused on the reduction of bicarbonate in electrolyzers or flow cells or flow reactors. And this really ties into CO2 utilization. Okay, and so where we fit in this value chain is that we want to take captured CO2 solutions and actually convert those into useful chemicals and products. And so these types of units are called electrolyzers. This is where you're using electricity to take that feedstock and convert that reactant A into product B. And in this case, we're trying to convert CO2 into something useful. I think it's always a good starting point to look at what the benchmarks are for success when you're building out these types of reactors. And when we look towards industry of all the commercially relevant electrolyzers that are out there today, you'll start to notice a few key things. And one of them is that you need to have high reaction rates in your electrolyzer. That means you need to be operating at current densities of at least 200 milliamps per square centimeter. Of course, hydrogen electrolyzers, the PEM electrolyzers are operating at an order of magnitude higher than that. But I think you can build actually a pretty strong business case around electrolyzers that are operating closer to 200 milliamps per square centimeter, depending on how well the system operates. Another thing that's important is we need our system to operate efficiently. And for a CO2 electrolyzer, we really need to get these systems operating at voltages below 3 volts. And if you're involved in this community, you will notice that in many of the literature studies, it's simply not, the voltages, the full cell voltage of the system is simply not reported. And in many cases, it's because those voltages are north of 5 volts. And so the energy efficiency of CO2 electrolyzers that are being developed in many cases are just too inefficient for commercial operation. So we really need to get those voltages down. That's a big one. We want to have high product selectivity. We don't want to be making a mixture of products. If you do that, that just adds to the cost on the back end in terms of separations, and it also reduces the overall efficiency of your system. But we now have lots of reports out there of fairly selective CO2 electric catalysis. So that one I'm pretty confident on, but as we get to higher value carbon products, C2+ products, that problem becomes ever more daunting. We also want to have high CO2 utilization rates. And that means that every time we have CO2 pass across our electrode, we want to react as much of that CO2 as possible. And in many of the state-of-the-art CO2 electrolyzers today, that utilization rate is less than 20%. And we really need to get that closer to 100%. And then finally, we need to have high durability for our systems. And when we look at the electrolysis that's used in the chlor-alkali industry, the chloride industry. Those systems, those electrolyzers operate for at least 4 years, and in some cases they last for 16 years. And they'll go through periodic shutdowns for maintenance requirements, but they are not dismantled and completely refurbished. So we really need to have these systems operating for a long time, and that's one of the challenging things to study in this area. I just want to highlight that there are actually no low temperature commercial CO2 electrolyzers that are available today on the market. Okay, and so there's no system that has checked off all those boxes on the previous slide. So there remains a lot of science and engineering to be done in this area. With that said, there's been incredible advances in this community over the last few years. And one of the overarching observations from all of this is the fact that the best CO2 electrolyzers that have been reported to date use gaseous CO2 as the feedstock. And the reason this is that if you design an electrolyzer in which you're feeding it with an aqueous feedstock, you can pump as much CO2 as you can into that liquid feedstock, but you're going to be confined by this low solubility limit of CO2 in water. And so as a result, you're simply starving your electrode of CO2 once you start operating at high current densities. So liquid CO2 is just fine at low current densities, but if you want to get be operating at well north of 200 milliamps per square centimeter, it's going to be tough to get enough CO2 to that electrode. And so a way to counter this is that you simply replace that liquid feedstock and you just pass a pure stream of gaseous CO2. And in this case, we're just dealing with 1 atmosphere of CO2, and you can see that we're getting a doubling in the performance output of this electrolyte, of this electrolyzer. And so it's a very simple modification, yet you get this step change in improvement in performance. Okay, so feeding gaseous CO2 is better than feeding your system with liquid media saturated with CO2. By extension of this is that if you want to get as much CO2 to the electrode as you can, then you might as well be operating at higher temperatures or higher pressures. And so we and others have shown that as you start to pressurize that feedstock going into your CO2 electrolyzer, you can start to reach even higher current densities. So 1 atmosphere of CO2, you're operating at less than 100 milliamps per square centimeter. But as you start to really feed a lot of CO2 in the system, you can get to much higher current densities. And now we're talking about current densities that are really commercially meaningful. So again, we're reaching that 200 milliamps per square centimeter. But I think we really need to take a step back and think about the entire CO2 value chain before we invest too much into the notion of feeding gaseous CO2 into our electrolyzers. And so this exercise is actually just going to take a look at taking atmospheric CO2. So you have a dilute CO2 source all the way to the final product if we're going to use a CO2 electrolyzer. Okay, so the first step is that you've got CO2 that's going to be captured in an absorber. So you've got some CO2 lean sorbent, and if we're using air capture as a means of doing this, you can imagine that you're reacting some base. So you've got hydroxide reacting with CO2 to form carbonate and bicarbonate. And then that CO2-rich sorbent then will go around, and then you need to strip that CO2 from your sorbent. And that's really the big energy-intensive step that's really challenging when you look through the economics of this process. So the reaction between hydroxide and CO2 is spontaneous, so that's not energy intensive. But taking CO2 off that sorbent is energy intensive. But nonetheless, what this step does is it closes the loop because you regenerate your caustic solution, so you can go back and capture CO2. And now you're releasing pure CO2 And now you can start to do something interesting. Now, as I said, if you want to get to higher current densities, then you want to invest into a compression step. And so there's an energy penalty associated with that. And then you have your CO2 electrolyzer, then that would take that pressurized CO2 and convert it into products. All right, now we've got these challenges where we've got these low CO2 utilization rates. And so you actually have a lot of that CO2 that you've just invested a lot of time in capturing and liberating it from the sorbent and compressing it. Now, a lot of that CO2 actually just passes right through your CO2 electrolyzer without passing through, without going through a reaction. So that's one of the big challenges, is that now you've got really a small fraction of your product is actually being formed. And then on top of that, you've got this parasitic reaction in which the reaction with CO2, so the incoming CO2 can then react with any base that will naturally be generated at your cathode catalyst surface. And so in doing that, you then form bicarbonate, and bicarbonate itself is actually is electrochemically inert, and that can be converted into carbonates. But bicarbonate and carbonate, this is not going to be converted into fuels. These are electrochemically inert species. CO2 is your electrochemically active species. That's what you want to convert into product. And again, you have base as a byproduct in these reactions. And so you're going to generate base, which will then want to be looking for some CO2 to react with. And so this is a parasitic reaction that is really challenging to manage. Okay, and we put together this Sankey diagram just to drive this point home. So you're feeding your electrolyzer with CO2. Again, you got 85% of that CO2 isn't even reacting with anything. So you've got this low CO2 utilization rates. And then the CO2 that does react, half of that ends up as bicarbonate. And then you're left with a pretty small fraction that ends up as your CO2 RR products. And so these are just some of the big challenges that we need to address as we build out these electrolyzers. And this really brings me back to the title of the talk, and that's the electrolysis of bicarbonate solutions directly. And so this is something that we started looking at a few years ago because of these challenges around CO2 electrolysis that I've just laid out. And the entire thesis here is that if we are using hydroxide solution to capture CO2, you're going to be forming a bicarbonate, bicarbonate product. And what if we could actually just take that liquid, that aqueous liquid bicarbonate product that comes off of your absorber and feed that directly into the electrolyzer. And if we could do that, this would be really effective in allowing us to close the loop, because what the product that would come out of our electrolyzer is base. And so that base would go back into the absorber and capture more CO2, forms bicarbonate, comes back, gets electrolyzed, you form a carbon-based product, hydroxide goes back and goes back and reacts with CO2. So conceptually, this is quite an appealing idea here, because what we're doing is completely knocking out this energy intensive stripper step. We're knocking out the compression step, and it may give us an opportunity to actually get to higher CO2 utilization rates and form more product, leaving us with less unreacted CO2. And I'm going to show you some data that this is in fact something that we've been able to realize. Okay, and so this, I'm going to show you through the rest of the presentation our work around this, but we're pretty excited about this because we seem to be getting some data that really points to us being successful on this front. The other thing that motivated us to look at this particular system is that designing, engineering, maintaining an electrolyzer with a gaseous feedstock is way more challenging to operate and build than an electrolyzer that's fed with a liquid feedstock. And that's my opinion, and it's not necessarily going to be an opinion that's shared by everybody. But anytime you are relying on a pressurized system, you have to invest a lot more resources into the seals of that system, and that just really can complicate the design of the electrolyzer. So this was another motivating factor. It just seemed to me that an electrolyzer that could actually electrolyze liquid bicarbonate would be a lot easier to build and maintain for a sustained operation than something that was being fed with gaseous CO2. Yeah, so the punchline is that when we first started building our first pilot reactors with bicarbonate feedstocks, we weren't getting great data, but it actually worked, and it worked better, to be honest, way better than I imagined it to work as a first set of experiments. And so these were experiments that were first done by my graduate student, Tengfei Li, who's now doing a postdoc at Cambridge and actually is looking for an academic position in this particular cycle. And so he initiated this work. And you can see that the performance metrics for this system are not great. And so what I've done here is I've plotted selectivity as a function of current density or reaction rate on the x-axis. And so the best electrolyzers on this plot are going to be up towards the top right. And the top right, this is where you have really selective conversion of CO2 into products at high current densities. And so the state of the art over the last year has been, there's lots of reports now of us being able to hit current densities over 300 milliamps per square centimeter. It's our group, Ted Sargent at Toronto, Zhao at Delaware, Wilson Smith, and others have all been able to hit these high reaction parameters. It took us quite a few years to get to this point. And but I also want to call out the Illinois group really for doing a lot of the great earlier work around CO2 electrolysis, coming out of the labs of Rich Massel and Paul Kennis. But our system here in orange differs from these other ones because these other studies all use CO2, feeding gaseous CO2 into the electrolyzer. This one here uses a liquid bicarbonate feedstock. And again, there's a lot of advantages to using that liquid. But the performance parameters aren't great, but I can tell you since Tengfei started working on that, Bill and Eric have taken this really to the next level, and we are now hitting performance metrics that are really state of the art. And again, something that's not often reported in many of these studies is actually the voltage of these electrolyzers, which is often well over 3 volts. And we're now able to build a system that's actually closer to 2 volts. So we're pretty excited about this, and I'll walk you through how we got there. Okay. The first thing to recognize is that there is this link between bicarbonate and CO2 capture and CO2 conversion. And all of this comes down to acid-base chemistry. So you have a proton reacting with your bicarbonate species that goes into the electrolyzer, and that will generate CO2 and water. Now that CO2 is actually what gets electrochemically reduced. It is not the bicarbonate species. And I really want to highlight that because yes, we're feeding CO2 into our electrolyzer, but it's not this species that's reacting at the electrode. It's the reaction product of bicarbonate and proton giving us a CO2. And it's that CO2 that ends up getting electrochemically reduced into our carbon-based products. For this presentation, I'm just going to focus on carbon monoxide as a product. It's the simplest carbon-based product you can make. It's a 2-electron process. That means we're just using silver catalyst, but we can also make higher C2 plus X products just by changing the catalyst, but I won't focus on that in this talk. And so everything really does come down to what is going to be the pH near your catalyst surface. And that is the entire name of the game in building out these CO2 electrolyzers. You don't want to be operating at pH levels that are so low that you have such a high concentration of protons that you end up just generating hydrogen. But you can't be operating too high in which you don't have sufficient CO2 at the electrode. So you've got to find this happy medium in terms of what is the pH rate at the catalyst surface. This entire set of studies actually was really started by this simple experiment in which we took an H cell. All right, so we've got an anode compartment on the left-hand side. We've got a cathode compartment on the right-hand side. And the anode and cathode are separated by this bipolar membrane. All right, so now what we're doing is we're starting to pass a current through the electrodes. And when we do that, we start to see these bubbles that are forming right at the membrane, right here, right at that membrane. And I can't tell you how excited I was to see this video. I've never been so excited to see bubbles. Normally I hate bubbles because they're an energy loss in our electrolyzers. But these bubbles were exciting for us because they're being formed right at the membrane. And what that told us is that we were actually generating such a high concentration of CO2 by the reaction of protons going through the membrane. This is a bipolar membrane, so hydroxide is going to the left, protons are going to the right. So protons are going to the right through this membrane into the cathode chamber. Those protons are reacting with bicarbonate. That is our electrolyte medium here. So our electrolyte plus protons gives us CO2, and we're generating such a high concentration of CO2, we actually start to see bubbles. And the reason why I'm excited is that we were exceeding the saturation limits of CO2 in water right at this interface. And for that gave us an opportunity here, because it meant that we were able to form a higher concentration of CO2 at the catalyst surface than what you could possibly achieve by pumping as much CO2 as you could into that liquid electrolyte feedstock going into the electrolyzer. So the key here is that we are forming CO2 only at the catalyst surface. You're not saturating the rest of your solution with CO2. Once we identified that that's what we had in our hands, we've been confident that this was going to work. So we went out and designed a flow cell to be able to operate this at the higher current densities, and we wanted to be able to generate as much of this CO2 right at the membrane, which we call in situ CO2 or ICO2. And so this is what we did. And it's a very simple flow cell. We've reported this in a number of different papers now. We have our housing, we've got our flow plates. We're just using a commercially available nickel electrode pressed up against the commercially available bipolar membrane, pressed up against the commercially available silver catalyst layer against a flow plate. And so the reactions of interest to us today are at the cathode. Again, bicarbonate plus protons gives us ICO2, in situ generated CO2 plus water. Then in situ CO2 then gets electrochemically reduced into our carbon-based product. Okay, so we have not fed any CO2 gas externally into the system. We balance our reactions by doing standard OER in the anode chamber. There's been quite a lot of work by quite a few students and postdocs around this, and we've been going through and trying to optimize and understand what's actually going on in these electrolyzers. Playing around with membranes, playing around with catalysts, different electrolyzer architectures, and also figuring out what we can do with the feedstock as well. Just to summarize some key findings over the next few slides here. We're finding that higher mass transport leads to higher product formation. And so we can actually get to much higher performance metrics just by judicious design of our flow channels and making sure that we're optimizing for flow plates. And in our case, we're getting much better results with interdigitated flow plates than we are with some of these others that may work with gas phase CO2 or even standard liquid fed CO2 electrolyzers. We've been doing a lot of work playing around with our gas diffusion layers. And for those of you that are in this area, you know that there's just a wide range of parameters that need to be tested and studied, and this is what we continue to work on. But for example, if we've got a microporous layer, we find that we don't actually get a huge boost in performance, but without that microporous layer, we do get a higher performance. And so this is just an example of some of the things that we're finding. I really like this result from Bill Zhang, who's a postdoc in my group. This is a big deal to me because if you are familiar with building these CO2 electrolyzers and these GDLs, these gas diffusion layers, there's so many components. It's really tough to do reproducibly. And so every time my students are showing me data, I want to see error bars, but the error bars are massive, and it can be really challenging to elucidate meaningful structure property relationships from these types of studies. It takes a long time to really understand how to make them in a reproducible way. And so what I love about this the study here is that Bill just went out and said, you know what, let's simplify it. Let's just use a porous metal electrode. And so he did that, and he found this silver foam, and he etched it. And in doing that, he was able to double the performance metrics coming from this electrolyzer by using this metallic foam. And this result is beautiful because now our experimental error on these experiments is really, really small. Any student can make it. They're reproducing other students' data. It's not all over the map, and it's just so much easier to make and handle. And I strongly encourage the use of this for those of you that are in this area. Okay, but the big thing for us is that we wanted to get to lower voltages. And one of the big challenges that we had with our original design is that our bicarbonate electrolyzer voltage was operating at well over 3 volts. You can see at 200 milliamps per square centimeter, it was operating at 0.5 volts. Now that might seem high, but that's actually pretty standard for a lot of CO2 electrolyzer designs. But as you move to higher current densities, just with this standard commercially available bipolar membrane, there's just so much resistance that voltage just spiked, and there was no way we were getting up to an amp per square centimeter. So voltage really does matter. We've written up a paper around this. Voltage matters in a CO2 flow cell. We've built an analytical flow cell. We've shared the designs for it so people can actually go through and really track where their voltage losses are. And so this is something that we like to do with our flow cells, but this is actually a misleading title. I'm not even talking about the voltage losses, but what are the sources of the voltages in this flow cell that we're designing? So we've got a cathode layer, we've got an anode layer, and we've got a bipolar membrane. And so for the CO2 reduction reaction to CO, at the pH that we're operating at, that potential is 0.7 volts. And I'm now just talking about thermodynamic limits. OER at pH 14, 0.4 volts. And then we've got our bipolar membrane, which will have an inherent 0.83 volt voltage differential. And so as a starting point, we should be able to operate this electrolyzer at minus 1.93 volts, and yet our voltages were up at 5 volts. And so we needed to get this to be a lot more efficient. And so one of the things that we wanted to do is knock out this pesky oxygen evolution reaction at the anode. So let's get rid of the 400 millivolts by looking at other oxidation reactions. And one of the things that we've converged on, at least for a proof of principle, is the hydrogen oxidation reaction. And by doing that, we get rid of 0.4 volts in the system. Plus, we're going to get rid of a lot of that overpotential that's associated with the OER, because that's a 4-electron, 4-proton process. The extra kinetics requires more voltage. HOR, 2 electrons, 2 protons. It's a kinetically easier reaction to mediate. Looking at our bipolar membrane, again, the minimum potential difference here is 0.83 volts, but actually as you start to operate at higher current densities, that voltage starts to go to the moon. And this is something that we really needed to address. And so how we did this is we decided to replace that bipolar membrane with naphthalene. And now, in principle, we don't have any voltage differential across the anode and cathode. And so by making those two simple changes to our reaction chemistry, now the thermodynamic limit of our cell is 0.7 volts instead of that 1.93 volts. Okay, and so this is what we wanted to go out and do, and it turns out that these hypotheses were proven to be valid. And you can see that with this new electrolyzer, we can now operate all the way out to an amp per square centimeter. If I come back to 500 milliamps per square centimeter, we're operating at roughly 2 volts, and we've got data now that we're at 2 volts. And so this is a substantial reduction in voltage with the bicarbonate electrolyzer, but it also compares very favorably. At the time that we published this was probably 700 millivolts better than any other CO2 electrolyzer operating at high current densities. So we're pretty excited by this. Now, the challenge in the system is that we're now feeding hydrogen gas into our electrolyzer, and hydrogen gas is not naturally available. You have to make it. So there's a cost associated with that, and that's a fair criticism. And I don't want to land on using hydrogen at the anode in perpetuity, but I think as a first step, actually, I can build a business case around using this. And as we did a brief techno-economic analysis on this, we found that as long as you can get your hydrogen at a cost of less than $2.3 a kilogram, you can make this work. Now, that's still pretty expensive for electrolytic hydrogen, and we don't want to be taking hydrogen from SMR, otherwise we're really not solving any problems with respect to the carbon budget. However, there are industrial processes out there that simply flare hydrogen to the environment because they're too far from end users to be able to sell that hydrogen. And given the fact that we're just trying to capture atmospheric CO2, we can put our facilities anywhere we want. I can see some installations with this type of electrolyzer and it actually working out just fine. And I'll wrap up here around CO2 utilization. As I said before, with gas phase CO2 electrolyzers, the highest CO2 utilization rates that were reported are 20%. Many of them are closer to 10 to 15%. And so we really want to get those numbers higher, but this has actually been a challenge with gas-fed CO2 electrolyzers. We use our liquid phase bicarbonate feedstock, and we're now in the 50 to 70% range with our current configurations. So now we've got like more than a doubling of our CO2 utilization rates. And so that's going to lead to a reduction in our capital systems costs. And so this is why we think there's a real opportunity with this. And so my final slide is that my current conclusion around this is that bicarbonate electrolyzers will save the world. And I'm obviously being facetious around that, but I'm quite excited about it for a number of reasons that I've already laid out in this presentation. One is that we are knocking out a lot of the energy intensive steps in the value chain of taking CO2 from a point source or the atmosphere to a final product. Second, we're knocking out those processes that are also really capital intensive. So now I can start to imagine a plant that costs a fraction of the cost of what a standard CO2 to fuels plant would actually cost. And as we work through these numbers, the embedded energy in the carbon product with our system ends up being less than half of that of the system where you have to use a gaseous CO2 feedstock. Now, these are early days for us. I'm not saying that this is going to be the final answer, and we're starting to work with folks around modeling this so we can start poking holes in this entire framework. And I'm sure there's going to be some catches along the way. But right now we think things look pretty promising, and I certainly welcome feedback from this very diverse audience around energy systems on what the flaws are in our approach and what the opportunities are. And I'll just stop there and thank the team for all of their hard work and like to thank Total for their support actually of this project. And the folks that have been driving this are Danielle. She was actually one of she built the first flow cell for us, and she trained a lot of groups that are now very active in this area to build out their flow cells. And Eric and Bill, they're still in my program. And then Max has gone on to Opus 12. He's not in this picture, but thanks for your attention. Be happy to answer any questions.
Thank you very much, Professor Curtis. I do like the final statement that we're going to save the world. So that's very good. So we actually have just a few questions maybe you could address. I think the first question, maybe touched a little bit on it in the previous slide, but they wanted to understand the energy requirements for the kind of the reference system. So like how much are you saving by transitioning to this kind of, instead of using gaseous CO2, now transitioning into this bicarbonate system?
Yeah, I think that question was asked earlier in the presentation, and I think this slide actually provides an answer to that question. And so we've tried to capture it in terms of the embedded energy in every CO molecule that's produced, or every mole of CO that's produced. And so as we work through the energy efficiencies of these systems, the energy inputs of these systems, this is where we're landing. So there's obviously needs to be an energy input to make these products, but because of the higher CO2 utilization rate, we're actually able to we're actually able to have a much lower embedded energy. And this analysis is actually very conservative in the fact that we're not trying to overstate the product performance of the bicarbonate electrolyzer. In fact, when we went through and did this analysis, we were using data that we actually hadn't even, that we'd already proven out. And we were using CO2 electrolyzer data here that is something that people are striving for. So we're not actually already there. And yet our energy savings end up still comparing very favorably. I see the next question is around the CO2 purity requirements. Yeah, that's actually a great point that I didn't even talk about. And with a gas phase or a gas fed CO2 electrolyzer, you have to put some resources into making sure that that CO2 feedstock is clean. Otherwise, you end up poisoning your catalyst. We have done some studies on learning how these impurities impact the performance of our bicarbonate electrolyzer. And we find that many of these impurities that shut down a CO2 electrolyzer, they do not impact the bicarbonate electrolyzer. With that said, there was one impurity that impacted the CO2 electrolyzer that also impacted our bicarbonate electrolyzer, but of course I'm drawing a blank on which one that is. But at least we're just focusing on the purification of one specific impurity and not a library of components in which many of the CO2 electrolyzers are susceptible to.
Then one more question, just I think it's about putting things in context. So you talked about the kind of the voltage loss, and I think the question is about how much voltage loss is too much for a commercial application.
Yeah, so it's a great question. If you look at commercial alkaline electrolyzers for hydrogen production, they are typically operating in the 1.7 to 2 volts range, and that's at current densities at roughly a ½ an amp per square centimeter. And those are numbers that I'm citing from a system that I know of, and that was a product specification from 2017. So there've probably been a lot of improvements since then, but we'll say 2 volts at closer to an amp would probably be where it's at today. The PEM electrolyzers, they're operating at much higher current densities. And so what is the voltage of that system? It's dependent on what the current density you're operating at. But anyway, for a water electrolyzer, we're talking about 2 volts. There are other electrolyzer processes out there that operate in the 2 to 3 volt range. And that's just due to the electrochemical potentials of those reactions that they're mediating. I'm not currently aware of any electrolyzer operating north of 3 volts, but I haven't really done an exhaustive search on that. But the big thing is like, what is the energy efficiency of the system? So if you actually map out your thermodynamic potentials, and then what is the voltage of your system really operating at? It's that delta that really matters. And all of those electrolyzers are operating at over 75% energy efficiencies. Almost all of them are actually north of 90% energy efficiencies. And so for us, having a CO2 electrolyzer operating over 3 volts is just way too high. We really have to bring that down quite a bit.
Okay, and then just one final question. I think some people are really excited about what you presented today. So they want to know, beyond carbon monoxide, what other products can your system select towards?
Yeah, we've proven it. We've proven it with formate, and we've proven it with ethylene and a C3 product. I forget what it was, but we haven't spent too much time on that. I suspect a lot of folks will invest some time into figuring out what catalyst layer gives rise to different carbon products. What we're finding is that we're not confined to that. It just comes down to your choice of catalysts. So you throw in a copper catalyst, we're going to make CX products where X is 2 or more. But I also want to throw the caveat that all of the engineering design principles around that electrocatalyst layer and how it impacts carbon-based products, they're not the same for the gas phase CO2 electrolyzer as they are for the liquid bicarbonate electrolyzer, just because we've got different polarities of feedstocks. And so we can't simply take that information that exists in the CO2 literature and apply it to the bicarbonate electrolyzer. We're finding that we have to actually build out an entire new database of information.
Great. Thank you very much for those, the presentation, also for your great answers. If anyone has other questions, please feel free to reach out to Curtis.